Welcome back to Chapter 5. This is Part 3, Sex-Linked Genes in Humans. Now we're going to take things a step further here and talk in more detail about sex-linked genes in humans. That is, genes that are expressed depending upon the sex or the gender of the individual. Now we're just going to review a few things before we move on. Remembering that hemizygous males display the phenotype from recessive X-linked traits. We know that already. And that homozygous females display the phenotype from recessive X-linked traits. So for recessive traits on the X chromosome, females have to be homozygous to display that phenotype. Males are always hemizygous. Therefore, most individuals that show the phenotypes of X-linked recessive traits tend to be males. Now, just a few vocabulary words. Males are heterogametic, which basically means that they can form different types of gametes, one with an X chromosome and one with a Y chromosome, so they can essentially give an X or a Y to their offspring. Whereas females are what we call homogametic, because they can only give an X chromosome. All of their gametes are the same with respect to the sex chromosome. So let's look at the inheritance of an X-linked recessive disorder in humans. One we can think of is hemophilia. There are many human traits that we think about being associated with the X chromosome, and some you've probably heard of. You've probably heard of hemophilia. You've probably heard of color vision or color blindness, which we'll talk about in just a moment. Well, here we're going to look at hemophilia. Let's figure out how this works, how this is transmitted in a pedigree. Now, hemophilia is a recessive X-linked genetic disorder. Individuals with hemophilia have problems with blood clotting, and that their blood does not clot properly. So if we follow the recessive hemophilia allele through a family, we can see that females can carry this allele and pass it on to both of their sons or their daughters. So here's the key. So we're looking at females who are carriers, either known carriers or inferred or possible carrier due to the phenotype of their sons. So here we have females who are carriers who will pass on that affected allele to their offspring, whether it's the daughters. So here's a daughter here. She will be a carrier, or she can also pass on that allele to her son, and her son ends up being affected. So since males are hemizygous, all the males that inherit this allele, of course, will express the condition, while the females will only be carriers. Now, the only time the females will display this phenotype is if they inherit two copies of this allele, one from a carrier mother and one from an affected father. Now let's look at color blindness here, another X-linked recessive disorder. A lot of times we think about color blindness being more prevalent in males, and this is the reason, because this trait is carried on the X chromosome. Now we can use this example to think about supposing a family knows that an X-linked condition, such as hemophilia or color blindness, runs in the family. How can they calculate the risk that their offspring will inherit this condition? Well, what we're looking at here is the risk of this child, individual number 1 here, in generation 5, or the risk of this child, individual 4, in generation 4. What is the risk that they will inherit color blindness? Well, for a known carrier female in generation 3, this individual right here, if we know that she is a carrier, the probability that she will transmit that mutant allele onto her offspring is 1/2. It's a 50-50 chance, right, that she'll transmit the affected allele. Now from here, supposing that this individual, okay, is being the mother of this individual here, if this individual did inherit that mutant allele, there's a probability that she will also pass on that allele. That probability is also 50-50 or 1/2. Okay, now the male here will only pass on the Y chromosome, so he really has nothing to do with color blindness. So our final probability here is 1/2 times 1/2 times 1/2. Now the reason why it's 1/2 is because even though the Y chromosome has nothing to do with color blindness, supposing that he passed on an X chromosome, that perhaps he may have been, that may have the color blindness allele. Then we have our probability of 1/2 times 1/2 times 1/2. And the same rationale would go for this individual here. Now, we've talked a lot about the X chromosome. Well, what about the Y chromosome? It must have some functions, and it does. Now, we know from Morgan's experiments that suggested that the Y chromosome was necessary for fertility, but not sex determination in flies. Now, in general, so that is true in flies. It's a little bit different in humans, and we'll get back to that actually in the next video. In general, the Y chromosome does not have as many functional genes compared to the approximately 1,000 genes that we see on the X chromosome. As we already know, the genes for male fertility are located on this chromosome in humans as well as in flies, and that there are some common genes at the terminal regions of the X and the Y chromosome. Some of these we refer to as pseudoautosomal genes, meaning that since they are present here and here, they act like autosomal genes because there's 2 copies. Okay, so males who would have a copy of a gene at the terminal ends of the X chromosome, which they also have a copy of that gene on the Y chromosome, they won't be hemizygous. They will actually be either homozygous or heterozygous because these act like autosomal genes. Now, this concludes part 3. Please join me for our next video about part 4.